When a humble bard graced a ride along.
Okay, I guess we should start now.
To figure out what they are. So let's talk about FRBs. But first, we need to talk about radio astronomy in general. So I'll start with a little bit of an introduction to that and then move on to transients. So, as you know, radio waves are a form of light. So, if your eyes were sensitive to radio waves, this is the kind of night sky you would see. Now, you see a lot of dots over there. Those dots are not stars. Those are uh, black holes at the centers of galaxies, which are accreting matter. So, these are active galactic nuclei or quasars, as we call them. And those are extremely bright in the radio. Stars themselves are not actually very bright in the radio. And you see these diffuse structures, which are supernova remnants and pulsar wind nebulae, which are formed after stars die. And you see many of those in the sky as well. Now, if you keep staring at this sky, you'll notice that it is not stationary. It is not unchanging. It actually has a lot of transients. So, over the past decade or so, we have started discovering these really bright flashes of light coming from random directions in the sky. And some of them are really bright. They can be as bright as your cell phone signal, except that instead of coming from a cell phone tower 10, 15 kilometers away, these are coming from halfway across the universe. Okay, and how we know that they come from halfway across the universe is something I will come to in a moment. And these are not rare. There are almost 1,000 of them every day in the entire sky, which are detectable for our for the typical telescope sensitivities. And a few of them seem to repeat. That is also another important thing, which I'll talk in greater detail later. Now, what goes bleep in the sky? So, in the 1960s, we had detected these things called pulsars. Okay, they are pulsating radio stars, which is why they're called pulsars. They are basically neutron stars, which are the dense cores of dead stars. After a very massive star dies in a supernova explosion, the core of that star collapses and it forms a very tight ball, which is about the mass of the sun, or 1.4 times the mass of the sun. And the radius is just 10 kilometers. So it's a very small ball, the size of the island of Mumbai, and it spins very fast. Now it has often it will have a magnetic pole which is misaligned with its rotational pole, and there are beams of electromagnetic radiation coming along that polar axis. And if it so happens that it is aligned like a lighthouse, right, and towards us, then we can see the sweep of light going past us whenever we look at whenever it is aligned. So the animation on the top right is showing you this lighthouse kind of effect. When the beam is pointed right towards you, there is a very high intensity, and when it is not pointing towards you, the intensity is quite low. You don't see it at all. So you get a very sharp pulse of light. Uh, some of these pulses can be as narrow as tens of microseconds. Some of them can be as long as a couple of seconds. Now, notice that this kind of rotation will give you very regular repetitions. The moment of inertia of a pulsar is very high. So, these repetitions will come very, very regularly. In fact, some of them rotate so regularly that the timing is better than those of most atomic clocks. Now, you'll say, okay, we see these pulses, we have been seeing them from the 1960s. So, what makes FRBs different from these pulses? Well, that to understand that, we need to talk about dispersion measure. Okay, so when a pulse arrives from an astrophysical object and we see it in a radio telescope, it looks something like this figure on the top right. What it is showing you is the intensity as that is the radio power as a function of frequency on the vertical axis, going from about 1200 megahertz to 1600 megahertz, and time. Okay, so this is like a dynamic spectrum, if you will. And the bright part is the pulse arriving, and you can see that it arrives earlier at high frequencies and it arrives later at low frequencies. So this delay is because light travels at different speeds depending on its frequency through the interstellar medium. So when radio waves propagate, lower frequency radio waves travel slower, so they take longer to arrive to Earth. And the shape of this curve is very well understood from fundamental physics, and it is proportional to frequency to the -2. The total magnitude which you get from the top of the frequency channel to the bottom frequency channel is dependent on a unit which we call the DM, or the dispersion measure, and that is the integral of the number of electrons that the wave interacts with from the source to the Earth. Okay, so it is the integral of electron density along the line of sight. Now, this DM is not a priori known. We don't know what the DM of the FRB is going to be. So to find the pulse, what you have to do is you have to assume, let's try out a DM. There's one trial DM. You integrate the fluence at each frequency, integrate the flux at each frequency along that DM. So you assume that this is the curve, and you see what the time series looks like, and you see that there is a sharp peak here in the time series. So we detect the FRB, right? But if the DM was assumed to be wrong, then you would not find this. So you have to try out a lot of different DMs, and that makes it a computationally expensive search. Okay, and this dispersion measure itself is because it's an integral of the electron density. If you knew the electron density distribution, then it can be a proxy for distance. You can figure out how far the FRB came from, and that is what separates FRBs from pulsars. Now, almost all the pulsars that we know of are within our galaxy and in some of the nearby galaxies, the large and small Magellanic Clouds, right? And we have a fairly good idea of the electron distribution in the Milky Way. This plot on the left-hand side shows you a top-down view of the Milky Way, and the colors indicate the electron density. We are at a location about 8 kiloparsec from the center up towards the north, and we are in that spiral arm here. So if you tell me that I'm looking at a source in a particular direction, I can integrate this electron density along that line of sight, and I can figure out how much. Yeah, go ahead.
So the slides seem to be changing a bit late on our screen.
I see. Okay, I will keep that in mind. Thank you. Can you see two plots right now?
You can only see the one. I think the previous slide.
Okay, how about now? Does that
still
help?
Still the previous slide on.
Okay, hold on. Let me stop sharing and share again. Its frequency. Okay, can you see two plots now?
Yes, sir, we can see them now.
Okay, good. So you were able to follow up till this part, right?
Yeah.
Yeah, okay. So now let's talk about the electron distribution in the Milky Way. So as you can see on the left-hand side, that's a top-down view of the Milky Way. And we have a fairly good understanding of what the electron distribution looks like. So the color here tells you what the electron density is in that region. So if you tell me that there is an FRB or a pulsar or some other source in a given direction, I can integrate this electron density and figure out what is the maximum dispersion measure that the Milky Way can contribute in that direction. And it turns out that FRBs have a dispersion measure which is much higher than what the Milky Way can contribute. So this is on the right-hand side. I'm showing you a plot of the dispersion measure of various sources as a function of galactic latitude. So -90 is the galactic south pole, 0 is the galactic equator, and plus 90 is the galactic North Pole. So if you look in the plane of the Milky Way, then you get, there is a lot of ionized gas and stuff, right? So you get a very high dispersion measure. If you look away from the galactic equator and the galactic plane, then you're passing through the thin part of the disk, so you get very little DM contribution. So the blue dots are all the pulsars which we know of, and they're all within the Milky Way. And so you can see this very nice envelope which it forms. In the center, along the galactic plane, you get a very high DM contribution, and outside it drops. Now, FRBs, which are denoted by these red circles, have a much higher dispersion measure. Note that the vertical scale is in a vertical axis is on a log scale. So you have FRBs which have DMs of 1,000. Don't worry about the units compared to pulsars which have units in few 20 or 30 DM units, right? So where does this excess dispersion measure come from? It turns out all of that has to come from the intergalactic medium. Okay, and the intergalactic medium is extremely tenuous. There are very few electrons, and what it means is that to collect that dispersion measure, to collect the same amount of interaction, you have to go really far away so that the wave can interact with those many electrons. And that it turns out that these FRBs have to come from a cosmological distance, many gigaparsec away. And this eventually was verified because we were able to localize FRBs. So a handful of FRBs were localized very precisely, and we were able to find out the host galaxies, and then we were able to measure the redshifts. So this, the one on the top left is FRB 121102, which is a repeating FRB, as I mentioned. And that was the first one where we were able to pinpoint a host galaxy, and that came out from a redshift of 0.2. So at a distance of about 1 gigaparsec. Okay, and there are many others which are localized even at farther redshift. So the galaxies are fainter and fainter, and there are some which are very nearby. So there is the one on the bottom right, which is at a redshift of 0.03. So astrophysically, it is in our backyard. It's a distance of 150 megaparsec, right? So, but remember that there are only very few of these which are localized, and the host galaxy is known. The others are not well localized, so we don't know what galaxy they come from, but they all are cosmological. Now, because they are cosmological, what it means is that these radio waves are interacting with every electron and every magnetic field that they encounter from the source to Earth. Okay, and so they're traversing a great distance of the universe. So these FRBs have the promise to be excellent probes of the turbulence and baryon distribution in the universe. You can imagine that if there is an intervening galaxy or a galaxy halo and it has some clumps, then you can get scattering, and you can measure what sort of turbulence there is in the universe. You can try to see when helium became reionized at about a redshift of 3. You can also measure magnetic field distributions through Faraday rotation. So if there is a strong magnetic field around the FRB source, or if there is intervening magnetic fields, right, you can measure those. And this tells us about the origins of magnetic fields in the universe in the first place, and we don't really know how that happened. One of the other holy grails of FRBs is to find gravitational lensing. So if you have a lensed FRB, then you can get two images, and two images of the FRB coming to us from different paths, and then we can measure the time delay between them with great precision, and we can use that to measure the Hubble's constant. Okay, and you can actually possibly use it to measure Hubble's constant, the change in Hubble's constant. So you can actually measure the Hubble constant change over a couple of years, right? So while they're coming from cosmological distances, we don't really know what they are. Okay, and to use them as probes, you would want to understand what the intrinsic mechanism is, and what properties of FRBs are intrinsic to them, and what properties are extrinsic or because of propagation. So we have been trying really hard to figure out what these FRBs are. Now remember that we see all the pulsars from our galaxy, and we don't even see pulsars from within, from all of the Milky Way. We can only see it in our neighborhood of the Milky Way, because pulsars are not really that bright. But FRBs are coming from gigaparsec away. Okay, so they have to be a trillion times brighter than the brightest pulsars which we have ever seen. The crab giant pulses are the brightest pulses we have seen from pulsars. And these FRBs have to be a trillion times brighter. That's 1 with 12 zeros behind it. Okay, and we have simply no idea how to generate that much energy sustainably. So there are a lot of different FRB models. We set up a theory catalog called the FRB theory cat, which currently lists about 80 or so different theories. And most of these theories can be, you can make them into three different parts. There are three different parts you need to explain FRBs. One is where you store the energy, the fuel of your car, right? So you can store it in the magnetic field or the rotational energy or the kinetic energy or the gravitational potential. Then you have an engine which sources that energy from the reservoir and then extracts that in a very short period of time. Because remember, the FRB lasts only a millisecond, right? So you have to get that energy very quickly. And that can be done with magnetic reconnection or magnetic acceleration of particles or with shocks. And then there is a transmission which has to convert that energy, which is usually a kinetic energy or something, into electromagnetic radiation, which we can see. And that typically is done either by a synchrotron radiation or curvature radiation. What most of these theories do is mix and match these different components in different astrophysical scenarios. For example, you can have a magnetar, right, which is a neutron star with extremely strong magnetic fields. I'll talk more about that later. So you can have a magnetic field reconnection. So what it is like is basically you take two magnets, right, and you put the north poles close to them, north poles facing each other, and you press them together. So they will be repelling, but you still press them together. At some point, one of the magnets will flip and it will go clack, right? And that reconnection is basically what happens on the sun, for example, when you get a solar flare. And that can release a huge amount of energy, especially if your magnetic field is ultra strong. So that is one possibility. The other possibility is, for example, the coalescence or merger of two neutron stars. So if you take two neutron stars and they emit a lot of gravitational waves and then orbit slowly becomes smaller and smaller, and then they eventually collide, their magnetic fields are going to interact and they can produce an FRB. Similarly, there are a lot of different other exotic possibilities which are even less likely. Now note that this merger or coalescence scenario is cataclysmic. Like you have the merger once and it won't repeat again. Right? Whereas a magnetic field reconnection can happen again and again, or an interaction of an asteroid with a neutron star can happen again and again. So those models can explain repeaters, but a merger or coalescence cannot. Right? Now let me talk a little bit about magnetars in our own galaxy, because those are the favored models for FRBs. And in fact, there is a magnetar in our own galaxy which emitted an FRB last year, which I'll talk about later. So these are neutron stars, okay, with extremely strong magnetic fields. So these magnetic fields are 1,000 times stronger than regular pulsars. And these are the strongest magnetic fields anywhere in the universe. And these magnetars are known to emit huge bursts in X-rays and gamma rays. So the plot on the bottom right shows you the light curve of a giant flare which occurred in 2004, December 2004, where this magnetar from the other side of the galaxy emitted so much gamma rays that it saturated all the gamma ray detectors which were on satellites around the Earth. And it actually ionized the ionosphere of the Earth so much that you can see the pulsations of the magnetar in the ionosphere going up and down. It is a crazy amount of power that happened, from halfway across the universe in size. Right? And there are only 24 of these magnetars known. All of them are very young, less than 10,000 years old. Some of them would be even a few hundred years old. So they're astrophysically extremely young. And after about 10,000 years, their activity seems to die down. So they don't exist anymore. So with that, let's talk about how we find FRBs and how we try to study them. Okay, so we have a lot of different theories, but we want to understand how to separate out these theories and figure out which ones are correct and which ones are not. So the aim right now is for people all around the world is to detect more FRBs, you localize them precisely, you study the FRB locations in detail, and we want to detect counterparts at other wavelengths. Right? So, I mean, if there is an FRB alongside with a X-ray transient or a gravitational wave transient, that would be very useful for us to understand what FRBs are. So with that in mind, we built this telescope called the CHIME FRB. CHIME stands for the Canadian Hydrogen Intensity Mapping Experiment. And this is the team which is working on building the telescope and the pipeline to process the data. And this is set up in Canada. I'll talk a little bit more about that. And we actually, for the past 4 years or so, we spent a lot of time physically building the telescope. Everybody from undergraduate students to emeritus professors has dirtied their hands in the field and done a lot of firefighting and digging trenches to get this telescope built. CHIME is in British Columbia. It is on the west coast of Canada, and it is located in the Dominion Radio Astrophysical Observatory. So you see the old telescopes on the right hand side here, and you can see the 4 cylinders of CHIME on the left. CHIME is built as a stationary telescope. So there are 4 cylinders which don't move. They're 20 meters wide and 100 meters long each. And the walkway which you see on the top is actually the focal line. And underneath that walkway, there are 256 dual polarization radio antennas. Okay, and each antenna is sensitive from 400 to 800 megahertz. And the telescope because it doesn't move, it looks straight overhead. And as the sky rotates, as the Earth rotates, we sweep the whole sky. This telescope originally was built for mapping hydrogen in the universe, in the high redshift universe. And it was not built for FRBs at all. But because FRBs were so interesting and this telescope was mapping large areas of the sky, it became useful for FRBs. Now, why is that important? Why is it important that we can map large areas of the sky? Because even if there are 1,000 FRBs every day in the entire sky is huge, right? And old radio telescopes such as Arecibo, Parkes, Greenbank, they're meant to look at very small parts of the sky. They're meant to study small regions of the sky in great detail. So the chances of them detecting an FRB are very low. Instead, the new types of telescopes are meant to map large areas of the sky. So ASCAP, Utmost, Aperitif are scanning order of tens of square degrees in the sky. CHIME FRB observes 250 square degrees at any instant. So this rectangle is just to show the shape of the CHIME beam, but the actual area extends far beyond what the ASCAP area is. So this is the way CHIME looks at the sky. What you're seeing here is the radio sky, which is opened out into this ellipse. The circle in the center is the horizon at CHIME, and the middle ellipse is the CHIME beam. Okay, a single dipole on CHIME sees this ellipse on the sky, and as the sky rotates through it, it will see different parts of the sky through the day. Now, if you take 256 of these antennas in a line, then what you can do is you can make 256 different independent combinations, right? And so you can make different beams which are sensitive to different regions of the sky. And then what you can do is you can take 4 of these cylinders east-west and make another set of linearly independent combinations, and that would make 4 beams east-west. So what you eventually get is a video camera of sorts, right, which has 1024 pixels with 4 pixels wide east-west and 256 pixels long, north-south. Okay, now this would seem like a very small data rate, except that we are not scanning in 3 colors, RGB. We are doing 16,000 colors. Okay, so this data is divided into 16,000 frequency channels. So it turns out it's a huge amount of data. Now there are 3 different, actually this is an old slide, so there are now 5 different backends, but this is the 3 original backends that Chime started with. So you have Chime Cosmology, which takes data at a 10-second cadence that produces about 210 terabytes per day. Okay, and through compression you can bring it to about 1 terabyte per day, which is a huge volume, but it is nothing compared to what Chime Pulsar and Chime FRB do. The Chime Pulsar beams, they track all the galactic pulsars daily with about 6.4 gigabits per second coming through 10 different channels each, right? And the Chime FRB data is produced with 1024 FFT found beams with 1 millisecond cadence and 16,000 frequency channels, right? So it has a total of 1.5 petabytes per day, and we simply cannot save that data. So you have to actually search it in real time, figure out where the FRB occurs, and then save exactly that data. And that is done through a huge software pipeline that all of us wrote. And it has multiple stages, which are very inventively called L0, L1, L2, L3, and L4. And so this is just level 0, level 1, level 2, and so on. And what we do is a lot of digital signal processing, and you can see RFI excision quite a bit in this. RFI is radio frequency interference. Okay, so cell phone towers, TV stations, aircraft, helicopters passing overhead, satellites, they cause a lot of interference, and they have a lot of intermittent signals as well. And so they cause a lot of false positives, which we can mistake as FRBs. So we have to work very, very, very hard to remove all that interference. So in fact, for almost a few million signals we get, few million signals we get 1 FRB. So we have to make sure that our false positive rates are 1 part in 10 to the minus 6 or so to get a real FRB. So to do that, we have about 2 sets of clusters. This one is the correlator with 256 nodes, each with 1024 GPUs and about 33 terabytes of RAM. This is the correlator. It does all the correlation for the beamforming and so on. And that this actually handles a few % of the world's internet traffic. Okay, so the amount of data flowing through here is enormous, and this is built, entirely out of commercial hardware with a bunch of students and postdocs and faculty members working together. And the second part, to do the actual searching for FRBs, is done by the Chime FRB backend, which has 130 nodes with about 17 terabytes of RAM. And this does the searching for FRBs. Of course, all of this has to be powered with a huge amount of software, which was written by our team. So you can see that it has this Chime FRB collaboration. GitHub has 113 repositories written by almost, well, now it is 97, but earlier it used to be around 30 people. So there is a lot of collaborative coding and coding involved, which we have to do to make this work. Okay, so now you would ask, okay, that's all well and good, but what do we know after all of this? So let's talk about the results. So since Chime began, we have published a lot of results over the past 2 years. The first detection of FRBs at 400 megahertz, the detection of almost 7, now I think 24 or so new repeating FRBs. Then it turned out that one of the repeating FRBs had a periodic activity. So every 16.4 days, it would start repeating again. And I'll talk a little bit more about that later. Then there's a Galactic FRB from a magnetar in our own galaxy, which was the brightest radio event ever detected by anybody. And we had a repeating FRB in a very nearby galaxy, the M81, which I'm sure you are familiar with. And this year, earlier, about 2 months ago, we published our first catalog with 535 FRBs. So these are the these are the summaries of results from the catalog paper and the associated paper. I'm not going to talk in detail about all of these because we still have it's only a 1 hour talk, and you are a fairly heterogeneous group of astronomy enthusiasts. So I won't talk in detail about this, but if anybody has questions, we should feel free to talk about it. So the CHIME FRB catalog has about 535 FRBs characterized between July 2018 and July 2019. If you would like to see what the data look like, you can actually go to our webpage and play around with the data. It's just a bunch of NumPy files and stuff, so you can open it up in Python and see what the FRBs actually look like. Now, let's go back to how we distinguish between different models, right? And one of the things is you can ask about our repetition. You can try to look for differences in burst properties, whether the shapes of bursts at the spectra are different. You can ask if the locations and environments of FRBs can give us some clue to what they are, or if there are any multi-wavelength counterparts. There are no confirmed answers to any of these right now, but there are a lot of clues which I would like to share with you, because that also tells you how we try to study FRBs, or astronomy in general is like a detective game. You have to use the clues to figure out what is happening. So the different models which I showed you, they will occur in different host populations. So for example, the merger or coalescence kind of models will happen in old systems where the stars have had a chance to grow old, have a supernova. Then there are systems where you need two supernovae to form the neutron stars, and then the neutron stars will need time to come close enough to actually have the coalescence. So those kinds of scenarios happen in very old populations where the stars themselves are 100 million years or a billion years old. Whereas magnetars, as I mentioned, are extremely young systems, right? They're not more than 10,000 years old for their active life. So you would expect young systems to form in star-forming regions in young galaxies, right? Similarly, if you wanted to have an interaction of an asteroid with an axion nugget, asteroid with a neutron star, or an axion nugget with a neutron star, you want a young neutron star. So something where you have an active star-forming region is really important. Similarly, the more exotic models like cosmic string cusps, they are expected to be primordial. So in many cases, they might not be associated with galaxies at all, right? Similarly, these different models can produce different counterparts at other wavelengths. So you have, a merger or coalescence of binary neutron stars will definitely produce a gamma ray burst. It will produce a gravitational wave event, possibly an afterglow. A magnetar quake or a magnetar giant flare will produce a possible X-ray burst if it is aligned correctly. So there are a lot of different things that we try to measure. Similarly, there is repetition, which is really important. Now, repetition, or its absence is fundamental to a transient, right? If you hear a big bang, you would want to know whether the source destroyed itself, which is the bomb model, or whether it can burst again, right? It's a gun model. And that is really helpful because it allows you to do multi-wavelength follow-up. So if you know that there is an FRB in this location in the sky which emits bursts, you can observe that location with other telescopes and try to do more specialized studies. Whereas if you had a once-off FRB which never repeats, then you can't point other telescopes to it and hope to understand the phenomena. And so the first repeater was discovered by Arecibo back in 2012. This is FRB 121102, also known as R1, and we detected 11 bursts from that source at the same location in the sky with the same dispersion measure. That is important. So the dispersion measure more or less remains the same. There is a slow variation, but it more or less remains the same. And the plots I'm showing you here are intensity as a function of frequency and time, except that the dispersion has been corrected for. So all the plots which I'll show you here on after have had the dispersion corrected. Okay. Now, when you have repeaters and non-repeaters, the question you want to ask is, are they different populations? So if I'm making this schematic diagram with a population on the vertical axis and quote unquote rate parameter on the horizontal axis, are the repeaters like the orange model where you have single bursts which will never ever repeat and a bunch of repeaters? Or is it like the green curve where you have a bunch of frequent repeaters and you have a bunch of rare repeaters? Now notice that we have been observing for FRBs only for the past decade or so. So if there is a repeater which emits one burst every century, right, we would not be able to distinguish it from a single burst. So we can only put limits on how low the repetition rate can be, but we can never say that, oh, it will never repeat again, right? So there could be that green model, and you can ask whether they are different populations or two ends of the same population. And so the one clue about this comes from the bursts themselves. So it turns out that in the catalog, some FRBs are broadband and single component, okay, simple bursts. I'll show more examples later. And other FRBs seem to have multiple components. You can see on the bottom here, each FRB has multiple components and they are narrow band. They don't actually span the entire frequency band in the vertical axis, right? So you have simple bursts which can either be narrow or broad, and they can be scattered also, right? So some of them will show scattering, which is due to the turbulence in the interstellar medium. So the bottom two are scattered FRBs. And some FRBs will show extremely complex structures. So you can see these bursts which are after D-dispersion. Okay, so you're corrected for all the dispersion, but you get multiple components, right? And they always seem to be drifting downwards in frequency. And the rate at which they drift downwards, these components, varies quite drastically. But it's not always true that you get the downward drifting. Every once in a while, you'll get this very complex burst. Right? So this is a plot from a GMRT observation by my colleague Arun Naidu. And you can see there are 5 or 6 different components which go up and down in frequency without any particular pattern. So one of our students, Ziggy Plunis, for his PhD thesis, he divided FRB morphology into 4 different types. So you have a single component broadband FRB, you have a single component narrowband FRB, multiple components with the same spectra, or multiple components but with downward drifting. And it turns out that most of the single component broadband FRBs seem to be coming from as yet non-repeaters, whereas the other 3 seem to be coming from repeaters. And you can quantify this. This is just a qualitative statement, but you can quantify this. So you can do some data analysis and you can ask, what does the FRB spectrum look like? Okay, so you can have a very broadband power law-like spectrum. Okay, so on the vertical axis here is a parameter called spectral running. So a number closer to 0 means it is a broadband power law-like spectrum, and a number a more negative number means that it is a very narrowband Gaussian-like spectrum. Okay, and on the horizontal axis is the intrinsic width after removing scattering and other things. So it can either be very narrow, closer to 0, or it can be very wide, closer to 10 milliseconds. Right, and it turns out that the one-off bursts, which are shown in green here, have a very, very different distribution compared to the repeater bursts. So, and even if you compare all repeater bursts versus only the first detections of repeaters, you get a significantly different distribution in blue and in purple and orange, right? What it means is that repeater bursts are statistically temporally wider and spectrally narrowband. Okay, so repeater bursts do seem to be different from non-repeaters, but does that mean that they are necessarily different astrophysical origins? That is not necessarily true. You could have, if the rate of repetition is associated with how complex the bursts are, if there is some correlation, you have a younger or repeater or something with a more complex magnetic field, you might get more frequent repetitions of bursts, and they might be more complex. Whereas the older repeaters, or say something with a weaker or simpler magnetic field, might have fewer bursts and they will be simpler bursts. So some correlation of that sort might exist. So we don't know that they're necessarily different astrophysical origins yet. Now let's come to locations and environments. So this is one region of our studies where we had a lot of success in trying to understand the environments, because we are able to localize a few of these repeaters very precisely. So most FRBs are localized to a few arc minutes in the sky. Okay, so this the white circles in the plot on the right hand side show you a circle with 3 arc minute radius. Inside that there are hundreds of galaxies. We don't know which galaxy the FRB actually came from. So most FRBs are localized to regions of this size. But if there is a repeater, you can go back to it with some sort of an interferometer like the Jansky VLA or GMRT and try to figure out exactly where that came from. And it turns out that this first FRB was localized to a low metallicity dwarf host galaxy. And so low metallicity basically means that its gas is very pure hydrogen and it doesn't have other polluting elements like carbon, oxygen, and so on. So for astronomers, everything other than hydrogen and helium is metals. So this gas has not undergone a lot of star formation. It has not recycled because of previous star formation. So there are very few impurities. Now, you could ask the question, why is the first FRB that is localized in a dwarf galaxy, which is 10,000 times less massive than a Milky Way? If FRBs were associated with neutron stars, then there are more neutron stars in other places. Why would you go find it in a dwarf galaxy, right? And it turns out that the low metallicity is an important clue here, because low metallicity is associated with long gamma ray bursts and superluminous supernovae. And those are thought to have a millisecond magnetar as an engine. So when a long GRB occurs, that is expected to be powered by a millisecond magnetar. And the idea from that is that you could have a long GRB, and a few decades later, once the surroundings are become a little bit cleaner, this magnetar could produce flares, which would also produce, which we would see as the FRB. So we detected that FRB. It's a FRB 121102 is in a tiny host galaxy, which you can barely see on the top right. And it turns out that the next repeater which was localized was in a completely different kind of galaxy. Okay, so on the bottom you can see the other repeater, FRB 180916, which is localized to a spiral galaxy, which is pretty much the same size as the Milky Way. The metallicity is the same as that of the Milky Way, so it's not anything particularly different, right? So we don't really know what connects these two scenarios. One of the things that we are now trying to see is by observing it with the Hubble Space Telescope, and you can see that there is a slight this FRB lies at the star forming region of the galaxy, right? But it is not on top of the star forming region, it is slightly offset. Similarly, the other FRB 180916, which is in the spiral galaxy, is also offset from the star forming region. So it turns out that repeating FRBs are often seen in regions of high star formation, which is very nice. But the two well-localized ones are slightly offset, and we are still trying to figure out what that offset is actually telling us. We think that it is telling us that they are not really direct magnetars, but they're some sort of a binary system, but that is still under debate. Now let's come to multi-wavelength counterparts of FRBs. So as I mentioned, last year there was a galactic quote-unquote FRB, and there is this magnetar SGR 1935 plus 2154, which was being temperamental. It was sputtering around. It was showing bursts in X-rays and gamma rays since November 2019. Okay, and on 28th of April 2020, there was an extremely bright FRB which was detected by uh, CHIME, and also another telescope called STARE 2. And it happened when this magnetar was not even close to the peak sensitivity of CHIME. It was not on top of CHIME at that time. It was many, many degrees away, but it was so bright that CHIME could see it from the corner of its eye. And this was the first FRB from a canonical magnetar. We were able to identify that this FRB came from this magnetar, and it was not as bright as all the typical FRBs, because most FRBs come from cosmological distances. This one is coming, from our galaxy. So it is on the lower end of the FRB energetics, but it is still spanning the gap between pulsars and FRBs. What is more is that this FRB was accompanied by an X-ray burst with a multi-peaked X-ray burst. So the gray curve here shows you the X-ray intensity as a function of time, and on the bottom the orange line shows you the radio light curve. Okay, and you can see that there are two peaks in the X-rays which are very well matched with the two peaks in the radio. And it actually turns out that there is a slight delay which is measurable between the radio and the X-ray. The radio comes before the X-ray, and this delay is very telling, because that means that this emission mechanism should be a magnetospheric reconnection kind of event rather than a synchrotron maser event. But still there is a lot of confusion. We don't really know why there were so many other X-ray bursts without radio, and why there are, we also detected many radio bursts without the X-rays. Okay, so what makes that specific burst special? We don't really know. But what this does mean is that isolated magnetars can emit FRBs, and it turns out that the rate of magnetars can be consistent with the rate of FRBs, but they can't explain all FRBs. So individual FRBs have behaviors which are very, very different from SGR 1935 or other magnetars. So we don't think that all magnetars can explain all FRBs, but we do think that some FRBs come from magnetars. And as I mentioned, the time delay between the radio and the X-rays is really interesting. And that is actually telling us that the shock model doesn't work out in this case. The magnetospheric reconnection model is preferred. So as I mentioned, CHIME is detecting 2 to 5 FRBs every day, but the localization is only a few arc minutes, right? It is not good enough to identify host galaxies. So what we need to do is to do very long baseline interferometry. What it means is that you have to build telescopes that are really far away from each other, and then find, using the time delay between the arrival time of the FRB between, say, Algonquin and CHIME, you have to find the position of the FRB, right? So this is basically doing triangulation. And the aim that we have right now is that we'll get 1,000 FRBs localized in every year in the next 2 years. Right? So the construction of these outrigger telescopes is going on right now. So let me come back to what we are doing in India as well. So I'm a part of the CHIME FRB collaboration, so we continue to build on this, but we are also setting up more searches in India. So the upgraded JMRT in Narayangaon near Pune is an excellent tool for localizing repeating and faint FRBs, because it is exquisitely sensitive. This is the most sensitive low frequency radio telescope in the world right now, right? And the UT radio telescope, which is in the middle plot, shows you a cylindrical structure. So UT is similar to CHIME, but it is actually much larger. So CHIME is 4 cylinders of 20 meters cross 100 meters. UT is 30 meters cross 500 meters. So it has a lot more collecting area, and it can rotate. So it's a huge telescope which can rotate. Right? And that is being upgraded with a completely new set of electronics and computing system behind it to be able to detect FRB repetitions, measure their periods, and do a lot of scattering and scintillation studies. Thirdly, we have a plan of building a network of small telescopes, which would be extremely powerful for detecting very bright nearby FRBs. You really want to study FRBs that are nearby because they're easier to study with other telescopes, and since they are the brightest FRBs in the sky, you should be able to detect multi-wavelength counterparts as well. So we want to build a large network of telescopes which would look at the entire sky, not just a small part of the sky, but the entire sky, and have a continuous view of the sky. So it's like a monitoring system for the entire sky. So I'm not going to talk much about the GMRT high time resolution survey, but there are two different surveys which are going on right now with the GMRT led by Professor Bhaswati Bhattacharya, and the OT wide field array, which the upgrade of which is led by Professor Jairam Chengalur, who are my colleagues at NCRA, and they are doing a lot of great work in setting up the new systems and detecting FRBs. So I just wanted to shout out to them in case any of you are also interested in FRBs, you should come and join us. Okay, so let's talk about what it takes to study FRBs. Firstly, you need a curiosity for physics and astronomy. You also need a good understanding of classical physics. But what is most important is that you need the determination and drive to solve problems. You will run into problems and you have to solve them yourself. You have to find solutions by whatever means you can, and you have to keep at it. There is a lot of persistence that is required to solve these problems. If they were easy, somebody else would have solved them. They're hard because you're solving them because they're hard, not because they were easy. Thirdly, a lot of FRBs and pulsar science requires data analysis. So you have to have a good understanding of statistics, data analysis, and good programming skills. You have to be able to work with a large group and contribute good code to the data sets. It is no longer a case that you can do simple coding with on your own machine and do it all yourself. Science in today's time requires collaboration with a large group of people. And if you're interested in hardware design, of course, you need electronic skills. Okay, so with that, let me come to the summary. So we are trying to understand the origins of FRBs with many different tools. We are, as I told you, we are getting some hints from the burst morphologies and the locations and so on. But there are a lot of open questions right now which we don't quite understand. So we are now trying to localize FRBs, trying to detect a lot more of them. And we need help, obviously, from young people. And so you should come and join us. You should, we would like to have you work on detecting FRBs. With that, I will stop and open up for questions.
Okay. That was very.
Sorry, I can't hear you. Hello?
Hello.
Yeah, can you hear me?
Yeah, okay, I can hear you now, sir. So I want to ask, earlier in the presentation, you said that there are some pulsars with differently aligned magnetic field axis and rotation axis, right? So does that play any role in, breaking and reconnecting of the magnetic field, which might these
Right. So not really. I mean, sorry. Let's go back to. Right. So what happens with pulsars is that sometimes their magnetic fields are misaligned with the rotational axis, and if the magnetic field is aligned in such a way that it sweeps, if the pole sweeps our line of sight, then we see them as pulsars. Otherwise, neutron stars are extremely faint, so you won't even see them most of the times. So, or you might see them but not see the pulsations and so on. So the alignment itself doesn't seem to play a very strong role, whether it is in terms of its activity. But the complexity of the magnetic field does seem to play a role. So pulsars seem to have a fairly well organized dipolar magnetic field, whereas magnetars seem to have a very complex magnetic field. So it's almost as if somebody made a strongly twisted magnetic field and stuffed it inside the neutron star, and it is slowly coming up for the magnetars. And that activity of a magnetic field slowly unwinding through this conductive core, that seems to be driving most of its activity. Does that help, Abdul?
Oh, okay. Yeah, I did get your point. Okay, there's another question from our audience. On slide 5 in the galaxy diagram, there's a band near the center which has less electron density. So does that have anything to do with like the black holes over there, or some particular region of the galaxy? Or like, so is there any other reason for that?
Right. So I suppose they are referring to this region. I think this region is because it is not very well mapped. It is really hard to have dispersion measurements in this region. So I think that is the reason why that is sort of low electron density. But otherwise, I think there should be a fairly high amount of electron density. The black hole itself at the center of the galaxy is extremely tiny on this scale.
Okay.
Okay, are there any other questions?
Okay, I guess there are any more questions. So, okay. So there aren't any more questions anymore. So thank you so much for coming, sir. And it was a really informative and interesting talk. And we really enjoyed it. Thank you so much for coming and giving us such an informative talk.
Yeah, thank you for inviting me. It was a great pleasure. Right.
Thank you. So the pleasure was all ours.
Yeah. Bye, everyone.